Let's move on to the last talk of this morning session, which will also be the last talk of the online session of today's workshop. And let me introduce you to Andrew Moore from the Warwick Manufacturing Group, who will give a talk on driving MEMS into the automotive industry. Just a moment for me, sorry. So, right, just, thank you.
Well, good to meet you all, and thank you to ZeroAMP and everyone for inviting us. So, yeah, that's great. So, in contrast to the, I'll just do the clicker to make sure I don't go over old technology here. So, in contrast to the last one, this is very much sort of the sort of application side. So, you won't be getting any of the sort of detailed physics here, I'm afraid. So, my name's Andrew Moore, as you can see. I'm a principal engineer at WMG at Warwick University. And I've come with my colleague, Jonathan Sampson, who will possibly answer one or two of the questions that I can't. So, first of all, who are we? What do we do? Well, we're actually an academic department at the University of Warwick. And we were originally an offshoot from the engineering department that was focused very much on industry engagement projects. But we've expanded hugely from being one tiny little area to we now have about 10 buildings on the campus. We in fact have the largest number of buildings on the campus. We're aiming for at least Warwick domination. We have our own postgraduate students, masters and PhD, and we do a lot of work with SMEs, half a dozen people up to a few hundred, and supporting development under Catapult. We're also one of the Catapult centres for the UK. Research areas, I've listed more, but the ones that are probably most relevant here are from the energy point of view, which is batteries transport, rather than just simply cars. But along with that, we have a power electronics division, who sort of do sort of various work along wireless charging, and also sort of some of the industrial power banks, also rail, and you know, converters, inverters, motor developments, etc. We also have the large manufacturing automation area, and where we sort of engage with other partners. Jaguar Land Rover is probably the most well-known one that you would know of, but not exclusively. And we come up with different methods by which they can actually sort of manufacture more efficiently and also with better quality. Autonomous vehicles division, which is primarily looking at sensors, which actually would tie in quite well to the optical types of what we've just been listening to. So the safety and basically the detection and interpretation of the environment. And then finally, materials analysis and cybersecurity. Materials, steels, composites. Yes, there's still a lot of work you can do with steels, and steel is still a remarkable material. And then cybersecurity, where we can engage with government departments over that one. So contents. Just talk a little bit about the drive to electrification and some of the battery issues that we have. Some of the mitigations and our application, we hope that ZeroAMP will be able to assist us with, is this battery passport and why we need it. A little bit on MEMS devices, I'm sure you all know, and the concept and why we would like to use MEMS technology. Battery in use, our envisaged passport requirements, and then where Envision's microchip battery passport system sits within that. And then finally, what are the industry social reviews and paybacks? So, I've got some headings here. These are probably not exhaustive. Notice that the very small sort of items like sort of your bicycles, your scooters, etc., are specifically excluded here, because they will really sort of get trickled down technology from these areas. So we've got automotive, rail, light rail. If you don't know what light rail is, then basically trams are the same weight as the normal mainline trains. That means that they have to have a ballast of a similar thickness, sort of 1.5 meters or so. Obviously, that makes them very expensive, and only the richest of cities can afford them. Light rail, you only need a track ballast 30 centimeters thick. We, Warwick University, have been working on that, and that makes it available to small towns like Coventry, for instance. They're doing that. Buses, civil aircraft is a new one on the field. We all probably heard about some of the aircraft that the experimental ones. There's a couple of trains now in production, but other than that, that's right at the very beginning. And then we've got off-road plant and agriculture. Well, all of these, when you drive to electrification, somewhere along the way, you need batteries. Right, okay, we've gone on the wrong way. Okay, so basically I split that up, the EV battery into technical, reliability and commercial. You could argue that technical and reliability are much one and the same thing, but I've split it because technical essentially is how you're going to do it. Reliability is more to do from the user point of view, and then commercial in terms of how you can sell it. Right, so picking the first one up, which is technical. The biggest problem you have with batteries being a chemical reaction is obviously battery aging. Inevitably, they wear out. They can wear out as a result of temperature. In fact, temperature features quite strongly in there. And as a result of that, you end of life capacity variable. And even cell capacity is a manufacturing issue in terms of the quality when you manufacture the cells. Drive cycle variability, well, if you're going to put it in a sports car, you've got a very arduous drive cycle. Of course, temperature will feature in that. It'll get hot, so it reduces the life. And all of these factors, even the time you leave it fully charged and discharged, will affect the aging of the battery. The chemistry itself, of course. For instance, go back to the rail, you would use, say, something like a lithium titanate battery. That has tens of thousands of cycles available. However, in terms of energy, energy capacity, it's rather low. So a lithium ion or a lithium polymer will contain far more energy, but can do far less cycles as a result. And then system AC record. This is where the power electronics comes into it. The motor harmonics, etc. They will, you may put in DC blocking capacitors, but you sort of plug DC capacitors to block that to AC getting back. But it will affect the aging on the battery. And then the remaining useful life. More about that later. Reliabilities, I've split it up here. From an expected characteristic, as I say, it's a chemical reaction. It's going to wear out. So, provided you're here and your user knows that, that's not too much of an issue. But premature ones, of course, are a problem, both commercially and warranty issues, etc., etc. And we've also got hard or soft shorts. Well, you don't want a hard short in a battery because that's likely to cause fire, or potentially could. Soft shorts, you want to be able to mitigate them against, because that is effectively your reliability. From a commercial, the end of life application for a vehicle application is 80%. So it's a dead battery when there's 80% left, which is insane if you think about it. So this inflates the cost of batteries. You've got the cost of recycling and disposal. And if we were, ideally, you'd like to reuse that battery, to use up that 80% in a different application. But it's difficult to value assess that for those used batteries, and then difficult again to re-warranty that. So what have we got at the moment? We've got the variable battery aging. We track the characteristics by cell, pack, module, sensing. That's already occurring. We have our prediction algorithms, and we historically log at pack level. Right. But if we were to log the history at cell level, then you can disassemble these batteries, repurpose them. So, reliability with limited temperature and voltage sensing, that's all we've got at the moment, active balancing. But there are other things that we can sense, like pressure, and know more about what's happening within the cell. And then, currently, batteries just use a central battery management system that reports, detects, and logs at the pack level. So, from our commercial point of view, this premature end of life reflects our cost, and the cost of recycling and disposal goes on an 80% battery. You know, it's got a life still of 80%. Right, so the problem is that it's not, we don't have enough logging and monitoring that's sufficient for redeployment of these batteries, and we can't value assess them. You know, so you've got your pack, you take apart your cells, and we cannot value assess them sufficiently well that we can re-warrant them for second life. So what we need is a traceable history, and that's why we call this a cell passport. So the cell passport will reside within the cell, ultimately. And of course it's good for customers, because it gives predictability during the first life, but also it allows a second life and helps in order to be able to reduce the cost of recycling. So requirement, two primary areas, battery reliability and second life commercial viability. This is the ability to repurpose and resell on. So we need to know the history of use over time, current state of the battery health and predicted life, and as I said, disable it, be able to disassemble the pack and not lose all that valuable information. Where are we at the moment? Right. Well, this is Jonathan and his team have been putting sensors actually inside the battery cells. And you can see here we've got fibre graduating, and they've been measuring the temperature within the cell. Rather than infer, obviously the centre of the cell gets hottest. If you're going to mitigate any thermal event, you ideally need to know what's happening deep inside the cell. And so just simply putting a thermistor on the outside doesn't give you all the information, including obviously the time constant associated with it. And they built this external board, obviously based on silicon, as a proof of concept. And you've got your power supplies that's fed from the battery itself. You've got your power line, in this case it's power line communications that we're using, rather than having the myriad of wires, hundreds of wires that you will see in the battery pack. And you've got your ADC to sort of do the measure the sensing. Microcontroller, it's not shown there, but basically that microcontroller obviously contains memory, so you keep the local values. Okay, so the MEMS devices. Well, obviously we did our silicon implementation. It's not buried in the battery because it's much too big. One of the drivers really is that silicon is so very, very restricted in terms of its temperature range. And we're right on the cusp of starting to, In terms of automotive, it's quite a wide range of temperatures that you have to operate at. But if you compare that to aerospace, that's even worse. And so the MEMS devices are quite attractive as a possibility in that scenario. So essentially they're transducers or energy converters and miniaturized mechanical elements. And traditionally, they already exist, they're applied to these sort of areas, which is great too for us. You know, we need to do sensing too. And the RF switching, I noticed has been used for sort of variable capacitances, etc., tune circuits, and energy scavenging. So we want to take it to the next level. We want to use this as a processor itself. So ideally, we'd like to sort of cell-by-cell pressure measurement, you know, accelerometers, particularly in aircraft. That's very important. And possibly sort of thermal shock. We also want to, we'll have to sort of effectively hybridize, because we also need to perhaps look at color change on the electrodes. I don't know whether any of you have seen any of the YouTube videos on lithium-ion cells, but the electrodes themselves change color markedly with charge and discharge. So you can actually, rather than just seeing simple Coulomb counting, you can actually evaluate the amount of charge that's in a battery by looking at the color of the electrodes. So that's another area we'd like to try and look at. Electrolyte gassing detection, again, very important in aerospace. And in addition, we want our memory processing and power line RF. So this is what we'd like to see, simplified. Our battery cell, we've got our MEMS sensing, we've got our other sensing, which is probably going to be silicon-based. And then you've got your communications and processing and the memory. At the moment, I mean, we've got, what I showed you, we were talking about power line comms. However, we are doing research and using RF as a possibility, and looking at using these protocols, amongst others. That research is going on at the moment. Right, environmental challenges. This is the driver towards MEMS devices. You've got a really nasty corrosive electrolyte. Very, very, very dangerous, and to human beings, but also to most materials, including glass, which is unusual. So wide range of temperatures, -50 to +70. We shouldn't see higher than that because the batteries will stop working. And indeed, the lower temperatures, the batteries won't work at all. But nevertheless, we still need to monitor that, because that can be the external environment on the plane. Small package, so that we don't infringe on coolant storage capacity. So basically, how much space does it take? We want it minimized. And of course, all of these areas, including rail, high vibration environments. We also have magnetic fields there. Although obviously a battery has sort of two electrodes that are closely matched, and in theory, with the inductance of those, fields should cancel out. The truth of the matter is they don't completely, so you have a small residual field. And then the same with any, you know, whether it be silicon or otherwise, calibration and drift. So I won't read all through these, you can see them, but these were what we envisage as the passport requirements. I mean, the obvious ones, date of manufacturer, etc., to track from the very birth of the battery cell right through its life, and then your initial capacity. But we feel that you need to actually, this is probably one of the more interesting ones, that we need to actually track what's happening to the battery cell when the battery cell is in storage. There's been also, not a wonderful case, but there was a case, Nissan, I believe it was, about 10 years ago, where they were storing all their batteries if they'd been involved in accidents in cars and things, and then they would take them away for research. Yeah. And they stored this one particular one along with lots of other ones. And after a week, it decided to erupt into flames and took out the whole building. So the idea of actually being able to, waking up, taking a snapshot of what's happening within the cell, and then closing down, or during storage is actually very valuable. And you can imagine that multiplies up with the size of battery you would need particularly for aerospace. So integration challenges. Obviously, we've got lots of multiple devices. We want to integrate those into, ideally in one IC. I can't see that, but that would be the ideal, but to minimize that. Electromechanical sensing, obviously, if we can get that in, that would be brilliant. Silicon-based devices have this temperature limitations. And conventional MEMS devices offer some integration, and this is what we're changing. The other thing is EEPROM, don't forget, it's at 70 degrees, starts to leak, so you might start to lose your memory at elevated temperatures. So Envision's microchip prospect with ZeroAMP technology, we feel that it has good possibilities to be able to effectively miniaturize to the point where we can actually get these within battery cells. We've been told, it's -55 or better, but just untested yet. And to one point, this is 300 degrees. Now, if those cells, if a thermal event was to be averted, the temperature may still get to, very, very elevated temperatures. And that would retain the information in the case of the black box event. Particularly for we hope it would never happen, but realistically, we're in the real world. And we would like, obviously, this FPGA functionality, and we've been told that there is that possibility and multi-layer stacking, which is also very valuable to us. The areas that we feel that they need to look at is magnetic field tolerance. And we also need to know, what FPGA array size they can get for our sort of functionality. Also, of course, these hostile chemical environments that we're expecting this to operate in or be shielded from in some way. Some way of implementing these sleep and wake-up modes so that we can operate them outside of when the battery is not in use, and of course our serial content implementations, be that RF or otherwise. And finally, mechanical packaging and vibration. What happened there? There we go. So, what are the industry and social user paybacks? Well, from the user's point of view, if they've got more predictable in the battery's first life, if they've got a more predictable lifespan, and they know that they get pre-warned when there's going to be a problem, that they know that vehicle is still going to get them home, or how many hours they've got left before they have to do something about it, that's useful in itself from the passport point of view. Having more information, more sensing information. Industry and commercial, well, as I said, you can't call the battery dead 80%. It's ridiculous. We've got to do something about that. It's bad for the environment, it's bad commercially. So second life commercial viability, I think knowing the history of cells is key to that, to making that possible. But also known history over time. This is an interesting one. So if you sell your car to somebody and it's supposed to accelerate 0 to 60 in 10 seconds, and they go and tweak it and it does it in 3 or 5 seconds, when they come back and say, well, that battery's no good, you can have a look at the history and go, you're outside warranty. So there's other benefits commercially as well. And then easing approval for safety critical applications. And since I'm working in the aerospace sphere, that was the one that particularly I'm interested in. and it will make it easier for that to easy approval for aerospace. And then, of course, social and environmental field care, green credentials, we've got a longer, useful life for the battery. And if you think about it, if you can make them last longer, the waste issue becomes less as well. So if our battery in our car lasts 8 years or 10 years, if it's got another life, it could be extended to 30 years if it's used in a power bank in a house, repurposed. So it all helps the sort of social environment. Well, those were a couple of references I put up. Thank you. And any questions? And hopefully, oh, bingo! I think that must be the first time, John, I've ever finished on time.
Perfect. Thank you very much. So, a couple of short questions before we go for lunch. Yeah.
Andrew, I suspect there's a role for government in this. What interest is there from the government or the EU in terms of legislation around this?
Around the passport or around some of the application areas?
Any of them. I mean, you were talking about safety, black box, but also there's the environmental side of it, and all of those might be regulated by government.
Yeah, I mean, like I said, because I'm more involved in the aerospace side at the moment, it's more the sort of CAA that I sort of deal with. But yes, at the moment, I would say that they are still working on what they need, because I guess we all know as engineering, social science, that actually government legislating technology is a really bad idea. They should set the limits and then let technology work around it. So I don't know. Oh, do you want to?
If I could just add a little bit to that. The Automotive Council, for example, has set down a number of criteria for how batteries need to operate over the coming years. There's safety requirements. For example, I'm sure we've all seen pictures where Teslas and various other things have caught fire. You need to have a certain amount of time. You need to have notification. You have a safety issue going on with your battery pack, so you get people out of the vehicles. There was a case of a bus that caught fire in France, and the video went viral about that. But there's actually nobody on the bus, because I'm assuming from looking at the video they had good sensing. You have to do that, because you can hear a thermal runaway event occurring within the battery pack within a vehicle. You have very little time to actually get away from that vehicle, so you have to have pre-sensing. That's one of the safety criteria. Also, with your batteries inside, you need to know if there is something that goes off. There are ways that you need to stop that propagation from within the battery, and that uplead needs to be monitored as well internally. So there's all sorts of these other things coming in. In terms of recycling, another key thing for extending life is that there is now a requirement of batteries when they're manufactured that over 95% of the battery materials used must be able to be recycled and used again for future batteries. So that put constraints on manufacturers of the materials used, particularly now where we are going for very high nickel content cathodes in batteries and very low cobalt content. Strictly, you need to be able to recycle 5% of that cobalt, but it's getting actually ridiculous. You can't do it. So some of the constraints are stopping you from going forward practically. But supporting the circular economy as well, with this 80%, there's an awful lot of drive effectively to work out how to triage your batteries as well. I think Andy spoke about perhaps using the possible technology as one way, but also looking at how to thoroughly test these batteries quickly. Because at the moment, it can take hours to test, for example, a Nissan Leaf battery, because normally you would use charge-discharge profiles of 1C, 2C, 3C. So you can spend 3 or 4 hours triaging a Nissan battery, where got the Nissan Leaf is coming to the end of the first generation is coming to the end of its life, and Nissan are getting thousands of these batteries coming through. So we've also worked at finding a rapid way of triaging these batteries. So we use ACMPs, so we can get data very, very quickly to actually help increase the triage, or reduce the triage time for these. That's one aspect. But also, I think another important thing is insurance. I went to a couple of conferences recently where insurance companies are getting quite concerned about where we go with batteries, and they're not necessarily so keen to insure some of these vehicles. They want some kind of underlying confidence about how these batteries operate. So again, using MEMS devices, for example, will help give that information.
But some of it is still in its infancy. I mean, for instance, we had a query, didn't we, from the emergency services. Because the fire brigade, at the moment, the advice is clear the area and walk away from the fire. And that's the best that they can do with a battery fire. And they want better ways of mitigating all that. Do you have anything on that one? Well, yeah. So, anyway.
Another question?
I think it's a very interesting idea, but I believe this could also usually backfire. Because what we see now is like these 18650 cells have a circuit board at the end, which contains like a DW1P or something like that, and has over discharge protection and overcharge protection. It has like a little MOSFET already integrated on it that cuts off the contacts to the battery if it goes to overcharge or over discharge. But it's a separate circuit board. The circuit board is essentially stuck on top of the cell and encapsulated in the package. So you could imagine that somebody who's a bit, let's say, a malicious person gets their hands on batteries that come from a distillery, for example, removes the circuit board that is the battery passport, and then puts in a new circuit board that says, well, this is a new cell, and sells on the used cell as a new one, and according to the battery passport, it would indeed be a new cell. So how do you prevent that?
How do you prevent that one? Well, I mean, it's a good point. It's a good point.
Because we already see this happening, and I won't name a specific country in Southeast Asia, but there are already batteries on the market branded Ultrafire, which are essentially recycled laptop batteries. And they're sold as new 18650 cells. And if you actually do the test, they have like 50 or even less of their 50% or even less of their original capacity left. And there are instances where people bought these refurbished battery packs and their laptops went up in flames. Just because they are already being smuggled and they fall off a truck somewhere and then somebody puts a new label on the outside. So I think you have to be very careful with this kind of...
No, I will actually thank you for flagging that one, because it wasn't something I'd considered, I must admit, but now we will. The thing that jumps to mind is some of the tricks that some of the manufacturers do, where actually the removal of it actually damages the cell in some way. I mean, so effectively a mechanical interlock, I suppose. But no, you're absolutely right. And although I don't think it discounts it, because, like I say, initially you would never put these. I mean, the costs would be too high initially. So this would be a trickle-down thing anyway. So the aerospace area is a lot more regulated. It isn't perfect, because I know on aircraft, because having worked in the industry, that they have water sensors, because when they go to some strange airport, they mix water with the fuel in order to be able to challenge them more. So all commercial planes have a water sensor to check the water content of fuel. So yes, you will always get this sort of possible criminal activity. But no, thank you for that one. It's worth bearing in mind, that one. Yeah, a self-destructing cell when you say it.
Can I sort of interrupt on that one? In our sort of vision, you're moving towards a more miniaturized, integrated type approach with MEMS. So we'd be reducing the size of the circuit down to a point where you could make it an integral part of the battery manufacturing. It's just what you're saying. You have to rip it apart because the packaging of the chip as part of the packaging and the cell.
Yes.
And in effect, we destroy the cell by trying to remove it.
Thank you.
I think also from a practical point of view of taking these cells apart, it's very, very difficult. We spent quite a lot of time deconstructing 21700s and 18650s for our own instrumentation. And it's very difficult not to damage them. We have quite tight processes for what we're doing.
Good.
Just
Yeah.
in terms of, so I'm thinking from a personal point of view, what percentage of batteries in cars go wrong? Or what's it?
John, I don't know.
I do not know. I think,
More than they tell you, bro.
Actually, do I know? So thinking about laptop batteries, for example, some of the companies that produce cylindrical cells, I think the failure rate is incredibly low with that cylindrical cell design, because it has manufacturing integrity, and manufacturing faults are just absolutely minimalistically small. Very, very difficult to say. I would assume with Nissan as well with their Leaf. I can't think, somebody might say otherwise, they're going with Nissan Leaf that's gone up, but I can't think of anything. They do have, I've been to Nissan plant, and they do have quite a lot of quality control of their electrodes when they put everything together. So there's quite a lot of mitigation against that. The other thing is when lots of these commercial companies, they form these batteries in the first place, if you're going to have an issue, if you have a manufacturing defect in there, you'll pick it up very early on in the formation stage. And I've heard of companies where they will store their cells and batteries at very high state of charge, at a moderately high temperature for quite a long time to reduce any faults. So they do everything they possibly can before they release them out for public use to make sure that they don't actually have a faulty situation. But I think one of the biggest issues with these things is what we would term abuse afterwards. I've heard of people using these vapes with 18650s in, and they deliberately overcharge them because they can get a better vape out of them, and that apparently is beginning to cause issues. So you've got people interacting with these things, that will cause problems. Also, I've heard of a story where somebody was using a commercial, a standard thin-line 18-volt drill, and they dropped this drill, and the battery pack hit the deck. Thought no more of it. They put the thing on charge in their house, and they went away, and they came back and they didn't have a house. They could cause a fault within the cell, and that was that. That was actually over in Germany. It was actually an engineer who worked on lithium-ion batteries, or something. So yes, you do have that side of it.
Why 80%? Why 80%? That's, I'm not sure of the history of that, but that is what, I think it was to do with what they've probably done market research for vehicles to see what people would find as an acceptable range reduction. And that's where the 80% came from.
There's simply, again, I don't know the ultimate answer, but bear in the fact that people have range anxiety with vehicles, and typically, for example, you might buy a vehicle knowing it's got a range of 100 miles. If you've got 80% of capacity, then you're immediately down to 80 miles, so that will be quite restricted. But also in terms of the ability of a battery device to deliver power, the internal impedance resistance will increase with a battery over time, so you literally just haven't got that raw power. It's just as simple as that. And also your aging process will begin to accelerate after that, because if you've got resistance in there, then you've got your heating going, you've got your isolated losses, which increase as well, and that is sort of like the downhill of that battery in the end.
Yeah, actually on the slides it did say about sort of the power delivery and the impedance, but I didn't sort of go through it, but that was one of the things that we needed to monitor, because delivering power and energy are completely, well, they're related, but they're different things. Obviously, as you deteriorate the battery, then as John was saying, there's your internal resistance drops, so your ability to deliver your acceleration, your torque, your power.
I think it's also worth noting that if you're designing some kind of system that requires lithium-ion cells, batteries, there are two general types of cell that you can have. You can have high power cells, or you can have high energy cells. High energy cells, for example, will probably be suitable for storage applications on the grid because you won't necessarily need any fast discharge. If you're designing a ordinary car, you want high power, you want to have low resistance electrodes, you need to get that power out straight off that nice spread losses. So, and when people do design these devices, they think about exactly that concept of how that batteries will age in terms of resistance and capacity.
You mentioned a lot about aerospace. We're hearing a lot about hydrogen. Is aerospace really going to be battery?
I think there'll be a number of different types. I mean, SAF fuels are more possibility. I mean, personally, I have my doubts whether it's a great idea to grow crops in order to make SAF fuels. However, if once we've got enough sort of electrical production, then the idea of synthesizing fuel, by taking carbon dioxide from the air and seawater, and creating fuel.
That's same conferences as me. Sorry? Same conferences as me.
Yeah.
But I mean, people say it won't be mostly batteries in trains, in large aircraft or trucks, or even buses going hydrogen now.
Yeah. But I mean, one of the things Airbus, they've kind of quietened down. They said, the future is we're going to burn hydrogen. Now they've got a bit quiet on it. I must admit, I was fairly horrified when they said that. But if you obviously hydrogen fuel cells, brilliant. However, you can't get the power. You can use them. You will always either supercaps or batteries, one way or other. You need something that will provide huge amounts of energy, megawatts, for the period that is at least flying. Then you can trickle charge from your fuel cells, or even from a gas turbine. Yeah. That's the other possibility. You hybridize, you have a gas turbine engine that's running at its optimum efficiency, coupled to a generator to charge your batteries to get you up there and down. But then once you're up there, of course, it's using less energy. But, and that would help a lot as well. And that's using conventional forward fuel for SAF.
Really fascinating talk.
I do apologise. No, I did all right with the talk as well.
It's just that, they might be the lunch. So.